Okay, so this is week 4, and we just finished Ohm's law last week. I gave you some homework about Ohm's law, so please try to practice that a little bit. This week my goal is to repeat the characteristics of series and parallel circuits and combination circuits. So we'll do some practice problems on that, and it's also, I think there's some homework about that. So I want to repeat some of the stuff, make sure you get it, make sure it sinks in, and we'll move on from there to electrical components. But once we covered Ohm's law and Power law, resistances in parallel and series, we're done with the calculation part of the course, and we go to more terminology. Terminology is basically things that you have to learn about each components and characteristics. So it's going to be a lot of reading, a lot of name, but not a lot of math involved. After that, we'll move into motors, capacitors, the relays, what do they mean, how do they function, and it will be a lot of talk. I also want to finish, hopefully this week, the video. We did 2 portions of it. There's 40 minutes left, so I'm going to try to place that on Wednesday and Friday. And the reason I want to start with this video before we go into components, because all of these components depends on magnetism to function. So once we get the idea into our head, how does magnetism work, what is the function, what is induction, it will make a lot of sense to see the steps of how they work. Knowing the steps will help us know how to troubleshoot them. So we talked about series circuit, and we said it's used for 2 things. What are those 2 things? Safety. What else? And control. Safety and control is the simplest circuit. So safety devices, controls. Basically, we put every load right after the other, and we'll do a lab this week pertaining series and parallel circuit. That's what it looks like. So these are all control switches to control the motor, whether it comes on or off. And this is my voltage. If one of them goes out, the whole thing goes up. That's series circuit. And we said in series circuit, the voltage, what happens to the voltage? It drops. The first load is all the voltage. The remaining, you go to the next load, and the remaining go to the next load until you use up the entire voltage. So current growth for the entire circuit is the same. There's only one path. So if we have one path, if it does not divide, then current is always the same. We agree with that? No. And we said the resistance will add up. So you'll add the resistances as we go along. So 1 ohm, 3 ohms, 4 ohms, you just keep adding them up. So the resistance increase, the voltage drops, current stays the same. Again, you can write this on a note card and bring it to the test with you. I know when you get test anxiety, things disappear. So get a small card or an A4 sheet and write that down so it can remind you, okay, these are the characteristics and this is what I'm looking for. Voltage completely used by all the loads. So whatever voltage you have, it gets completely used and changes through each load. And we'll see that in the lab. We're going to go and measure the voltage. Everybody get the chance to measure the voltage last week? You know how to measure voltage? Everybody did it, right?
Yeah.
Everybody measured the amperage?
Yeah.
Yes. You feel comfortable with that?
Yeah.
You'll get more comfortable now. It's gonna be, you'll see the effect. So we're gonna, when we measure voltage, we go across the load with our prongs. When we measure amperage, what are we measuring?
Cable.
On the cable, what are we measuring?
Just 1 cable of amps.
But what are we looking for? Something invisible. The electromagnetic field, the magnet. And we saw when we put it around 2 wires, you get 0, right? Because they cancel each other out. And if we wrap it around, we'll get multiple magnets, and that's the role of the coil. So voltage drop, so we'll see that we have 118 coming from the receptacle. After the first load, probably you get 80, then 40, then 0. So at the end, it has to be 118 or 120. You cannot get more than that, otherwise something is wrong. You're getting extra voltage somewhere else. Parallel circuit, we said there is more than one path for the electrode to divide. This is the main characteristic of parallel circuit. The current will divide will converge into 2 or 3 and comes back again. It's very common for loads. And what did we say about resistance in parallel? Does it increase or decrease? Decrease. And we said something, we wrote it over there, that the total resistance is what? It's smaller than the smallest resistance in that circuit. So if you get something more than the smallest, you know something is wrong. Okay? So in that small circuit, if we add all the resistances, they should be smaller than the smallest. Everybody agree? Everybody understand? Is it confusing? Raise your hand.
The resistance decreases, what about voltage?
Voltage stays the same. And I said also, I gave you the example of the resistances for the circuit in your house. Every receptacle will have 118 because they are, yeah.
The total resistance divided by 1 or the total resistance divided by the number of total resistances you add?
Ask me again.
So you take all those resistances, you put them over 1, right?
No, you do the process. You get the total for them. The total is that long process. This is a schematic of 3 resistances in parallel, and this is also a resistance. This is the resistance. These are all 3 loads. What do we call these loads? This is consuming electricity. This is consuming electricity, and those 2. So these 4 resistances, are they in parallel or series? What makes you think they're in parallel? Because each one of them will get different, will get its own current. So this is going to come from here, and it will divide, this will divide, this will divide, and divides again. Then keep collecting back the currents, and the current here between those 2 points should be the same, but each one of those ones have different current. And each load will take the current it needs to operate. So these are in parallel. And what is our key? Sometimes in the schematic it looks kind of different. It doesn't look like the one we drew. If I were to draw this, I will draw it like this. And you might see it in a Is it the same? Yeah. So I want you to get familiar with all different types of schematics. This is called a ladder diagram. Why? It looks like a ladder. They have something called pictorial diagram, which they give you more details. So at the end, always follow the current and see what you get. Why are they putting the voltage between those 2 lines? Why is it in the middle? Why is it on a source? Because they tell you the electrical potential between those 2 lines is 120 volts. And this is very simplistic diagram, and you might find it on some ACs or some components where they tell you what are the major loads and how they are connected. Here, let's look at this circuit again. That's a very common circuit. And what do we have? Compressor, condenser fan motor. What are these? Contactors. We'll know what a contactor is. Probably Bill told you. What's a contactor? It makes a contact based on a command. It's a relay. We'll talk about that in the whole chapter. So basically, you get an order. So okay, turn the circuit on, and it will provide a contact for you. It will grip and make a contact. And you will hear that click. When you turn the AC on, you'll hear a click. That's the contactor. So I'm going to turn the AC now, and you're going to hear it. It's very loud because it's usually more than 15 amps. Heard it? That's the contactor, not the compressor. So that's it. It's very loud. It's a little bit scary because there's a lot of power going through it. Did Bill explain to you what is the difference between a contactor and a relay?
Says the size.
Yeah, excellent. Remember this. The size of what? Not the size, physical size. The size of amount of amps that goes through it. So in your car, if you have probably everybody has AC or control panel. You turn the AC on. You think you're turning the compressor on? No. You're turning a relay, you're telling it to go make the contact. And when you open the hood, there's a big fuse box, and it has some cubes in it. What are those cubes?
The fuses.
No. What are the cubes?
The relays.
Relays. So your relays are small contactors. So basically, you're turning on your board, which is low voltage, and it will make a connection in the relay, and the relay will connect the high voltage. And why do we do that? Because we want to make sure that we get the right contact in the right place, and eliminate also the spot possibility. So, contactors, are these two in parallel or series?
Parallel.
What's that series? Look, are they getting the same current or different current? Yeah, so they're in parallel. So, what about these three? Are they in series or parallel? Series. What about these three and these two? Are they in parallel or series? Okay, you're getting it. Anybody has any doubts? Maybe if I explain a different way, you understand. But it seems like everybody got it, so we'll move on. So calculation is usually done by equipment design. Current draw determined for each part of the circuit depends on the resistance of the portion. So we said every portion of the circuit will have its own current. The current draw depends on the resistance. How do we know the current draw? By the resistance and voltage.
The total resistance is the smallest.
If they give you the resistance and the voltage, would you find the current? How? Ohm's law. So Ohm's law will tell you how much current you're supposed to be drawing. And if you're not, how do you go and check if that current is being drawn or not? No. Use the clip-on meter. So if I did the calculation, it's supposed to be half an amp, and you flip on the ammeter, and it gives you 0.3 amps. Something's wrong with the equipment. If it gives you 8 amps or 0.8 amps, you know something's wrong. You're supposed to have the right amperage. If you have more amps, it means something is like drawing more, and that's not good for the circuit. Okay. Total amperage draw. Using Ohm's law, we're going to calculate the amps because they do add up. So as we divide, the main amperage will be the sum or the total of those amperage. So you add the amperage. And the resistance. If you have two resistors, this is the calculation for it. It looks kind of ugly. I like to go with the original idea. If you have more than one, again, 1 over R total equal 1 each log, and you kept adding up. But I find it's a little confusing, but if you find it easy, go for it. The way I do it, I remember to do these tips. So first, I flip, I put 1 over R total, which is this part. I get numbers, it's easier to deal with numbers than fractions. So I'll get a number here. I put the number of resistance in here. I keep this as 1 over RT. I get a total number for the resistances. And then finally, I'll bring back this to R total and divide 1 over this number. So there are many ways to do it. I'm sure there's an app for that. If you find an app, good app, let me know. Whatever makes it easier for you. You hardly ever have to do that, but I want you at least to practice 1 or twice here in this class, so you have an idea how it's done. Hopefully you will not have to use that in the field, but at some point, if you have to, you know where to look, how to look it up, and you know how it's done. I don't have an example here. Yeah, I have an example here. So this is how I start. I start the same way. I start with the resistance in series. I put R total equal R1 plus R2 plus R3. First, I flip, which means I divide 1 over each one of those things. Question about that? Second, I divide. So 1 over RT, 1 over 2, 1 over 5, and 1 over 4. Fractions is a little bit confusing, so I get from fraction to decimal. put them in the calculator. You can use a calculator. So I divided them. This looks much easier to deal with than fractions. You can also add fractions if you want to. That's up to you. But I find this method is a little bit easier. Again, if you have a different alternative way, online there's at least 4 or 5 of them to be done. So divide. So I have nice fractions. Nice decimals. I add them together. Again, most folks, the problem they run into is they forget it's 1 over RT. So somehow around here it just changes to RT. And you're gonna end up with 0.95, which is incorrect. Even though if I look, it's still smaller than the smallest resistance, but it's not correct. Finally, I will flip it, which you can use the function in your calculator, which is x to the minus 1, or you just divide 1 over 0.95, and you're supposed to be getting 1.0858 ohms. You can round up to the 2 decimals, and let's double check. Is it smaller than the smallest one? Yes, smaller than 2, so it is correct. It's very close to 0.95, but it's not the same. You think you can do this?
I got it.
Yeah. And again, if you feel like you're gonna forget it, write it on a card, bring it with you to the quiz, keep it with you. I don't mind. So take it step by step. And if you have an app, show me the app. I would love to see how the app works. Probably the app has a lot of electronics in it, so people who do electronics and circuit probably need to use this a lot. Okay. Voltage drop. Does the voltage drop in parallel circuit?
Parallel?
Yeah.
No.
No.
It stays the same.
No, it stays the same, so it remains the same. Combination. So we have a lot of combinations everywhere we go, because of course we want to have some control, right? There's some control going on, and there are some safety switches. So we're gonna have some series circuit and some parallel circuit. So it's always going to be a combination. This is a combination circuit here. And does it look overwhelming? A little bit. But after you stare at it for like a minute or so, it will make sense. So this is what's called a ladder diagram. What is L1? Hot. L2, neutral. So this is my voltage drop between these 2 circuits. If I put my prongs here for the voltmeter, I'll find 118 or 120. Okay, what about these 2? Are they in series or parallel? Series. These 4. What about these 2 circuits? Parallel. Excellent. These 2.
Parallel.
Excellent. These 3.
Parallel.
All right. So recognizing it is not that difficult, and that's why they provide us with the ladder diagram, make things a little bit easier. That's a combination. So they're used for most components, ACs, furnaces, boilers. They'll always have a combination between circuit, series, and parallel, and we'll see them in action. And this will make a lot of sense once we do it in the lab. Trust me, after doing it in the lab, it will make a lot of sense. We'll do the math here, and we'll go there, wire the light bulbs, and measure the resistances, and it will feel really great. Take a video if you want to. Actually, yeah, maybe tomorrow we should make a video of the lab. Thank you. Let's put it on YouTube so you can watch and see how the voltage drop and how the amperage drops as well. Another combination circuit. Again, every schematic you look at it at the beginning looks overwhelming. Even for me, I've been looking at them for years, but you look at it the first time, and you have to get over the overwhelming factor and take it from the voltage. Voltage drop, compressors, 2 contactors. This is a small circuit in parallel. Motor. What is this?
Transformer.
Yeah, transformer. And the reason they put it in different circuits is they tell you this is low voltage circuit and high voltage circuit. What do you think the low voltage circuit is for?
Control.
Yes. What is the usually the low voltage? How much? How many volts?
24.
24. And why do we need low voltage for control? It used to be, it wasn't always low voltage,
So
Yeah.
grandma doesn't get shot.
because that's what you're touching, and that's what you have in your house. You want low voltage because it's less dangerous, and you want the high voltage in the equipment. And the more low voltage you have, the safer and also less power consumption. You think it was possible to have your phone be this big without low voltage? No. Look at the mainframe and look how much energy they use. So the smaller the wire, the low voltage you have, the less power consumption and the least size you can do. And at the end, all what you try to do is just control, which is kind of binary. We'll talk about that when we do relays. It's 0 and 1. You're just making decisions. You're not moving anything. Just making decisions based on circuit on and circuit off. Combination circuit, there's more examples in the book for combination circuits, but I think that's enough. We'll watch the video again, and please try to focus a little bit, even though the video is a little bit corny, but the idea that I'm trying to get to you is the magnetism and how did it come about.